So this purpose of conducting this simulation is like this electronic component consists of chassis, covers, connectors, drives, capacitors, and this assembly experiences different types of loading like static, dynamic, and thermal. So in recent years, this testing and prototyping of these newer designs are simulation driven, and in order to reduce the cost and time. So currently, like the task which we have taken for like this presentation is the thermal and random vibration loading. So the scope of the project is, as I first described, there are two cases which we have taken, thermal simulation and random vibration simulation. So this is going to be more on study the electronic component to verify and validate the design, and also study the behavior of the electronic assembly for these two load cases. So the first case where we will be like identifying the thermal hotspots, and we would be also like working on the reduction of temperature based on the countermeasure suggestions. And the random vibration simulation where we do model and random vibration response analysis, where we would be like studying with the customer provided power spectral density curve, and also the outputs such as stress, displacement, acceleration at 3 probe locations as suggested by the customer. So this is the model where this electronic unit assembly will be like placed in this location as a part of countermeasures. So we have like modeled with typically with solid hexa elements and also shell elements, and this modeling strategy is more of like after meshing we proceed towards thermal simulation with natural convection. We have not considered radiation phenomenon, and at ambient temperature of 70 degrees centigrade, and conductivity and contact conductances are considered, and natural convection is defined for the external surface, and wattage loading is applied on the electronic components in the key location where the heat is generated. So the suggestions are like more of less than 105 degrees centigrade is the target. So convection is applied all across the exterior surfaces, and the wattage loading in the typical PCB heat generating units as indicated. So this is the typical temperature plot without fins, and we have seen that this temperature contours and hotspots close to 354 degrees centigrade without consideration of the fin structure. And when this component is placed on this structure with fin, we have like observed that the temperature has reduced less than 105 degrees centigrade, and this was the like structure which was like proven and safe to be like mounted on this unit. The second load case is of random vibration response. In both of these simulations, the key challenge was for us to simulate the structure with the exact mass distribution and mass correlation, where the structure has to be like exactly like matching with the distribution of masses as that of the physical unit, and also it has to be like simulated to the exact mass per each components. So apart from mass distribution, that the mass distribution is done by adjusting the density, and lumped masses are applied onto PCB structures for the child parts which are not of significant to model it discretely, and we have constrained the model at the mounting locations, and material properties such as Young's modulus, Poisson ratios are applied, and we have performed model analysis and random response. So the base acceleration is given at the mounting locations for X, Y, Z and X, Y, Z combined directions. So as indicated, these are the 4 mounting points where the loads are also applied, and this is the power spectral density curve applied at the mounting locations. So this is the typical mode shapes after we distributed the mass and matched the mass with the physical structure. So yesterday there was a question where how do you decide the probe location? In this case, customer has given the probe location, but these mode shapes can actually help you to decide the probe locations. So this, as I told, it was 3 locations were there in terms of probe locations, out of which we plotted close to XYZ direction, and also combined XYZ combined for acceleration, Van Mises, and displacement plots. So in all these 3 probe locations, we found that the second probe location was observed to be peak location, and even that peak location I have just represented here as a snapshot, and this acceleration was plotted. Van Mises stress also was well within the allowable limit, close to 120 MPa, I remember. So in terms of thermal analysis, it was like excessive temperature generated was like reduced by usage of the finned structure, and this inclusion of fins actually reduced the overall temperature below 105 degrees centigrade. And this random response analysis, we tabulated at 3 probe location, out of which the peak was found at one of the probe location, which was again like well within the permissible limits. So over a period of time, by doing these type of similar activities, we have developed expertise in even not only doing this thermal and random excitation response analysis, we have even developed expertise in creating fabrication drawing and considering manufacturing feasibility, and we also like collaborates in iterative procedure with customer in qualification of the electronic equipments by actual testing. So as and when the design reviews happen, we redo the analysis and make sure that the actual testing correlates with our FEA analysis results. That's all. Thank you.
Your use for this?
Material, it was there were different material structures like PCB structures. We actually like did not get enough details by literature.
I think the damping value which you used is a bit less.
2% structural damping.
Yeah.
Yes.
I think that's less. It's small.
No, predominantly yes. In steel structures, we use 2%, 3% structural damping.
It's some kind of plastic, right?
No, the chassis materials are having aluminum base, and we had a relatively like very less PCB structures of non-aluminum structures. So overall, the structure was predominantly having aluminum structure.
Convection? H value for the convection.
H value we have like taken very less. It was like less than 5 watt per meter square or so.
And if fan-induced convection, what kind of practice?
This is a natural convection. For a fan, for forced convection, you may need to use maybe more than maybe 40 or 50.
What is the maximum value of PSD you used as input?
This, as I told, this was like done with respect to all that band pass filtering criteria and all was done by customer, and we have received the PSD curve from customer.
How many of you are really active on LinkedIn? I said yesterday we will create a forum on LinkedIn. Any other we can create the forum on any platform. So is LinkedIn a good platform? How many of you are active in LinkedIn? Can you please raise the hands? So quite a few, almost. Is that a good platform, or you have any other suggestions to create this online platform? LinkedIn is good because we have already created a template there, and if that is good, we will create this forum. I can see a lot of people are asking a lot of questions, even outside people are discussing. There is a lot of enthusiasm that is generated. I want to take this really forward, and because that is what is needed for the country today. There is a lot of things happening in all the sectors we are talking, whether it is drivetrain or engines or automotive or electrical machinery. There is a lot of things happening, and people need to exchange their experience, exchange their views, and they have some doubt. They should have some quick access. Of course, these days things are very easy compared to 15 years back when the internet was not so well developed. So let's use this opportunity to develop better products. So I think we will make this thing in the next few days. Shortly, you will get this circular from us, on this forum. I request all of you to become members of these and then also circulate to your colleagues or peers who are in other companies who are not a part of this event, but still they can join. Let's make that community grow.